thanks for the kind invitation, and thanks to Bert and Ricardo for all the effort and sweat of setting up this wonderful workshop in these awkward times. Hope you're all well. Now, when I sat down recently and thought what to speak about and making some notes, I looked into the program and I noticed that, hey, there already was a title. And I thought, wonderful, that sounds interesting. So what we will be concerned with is probabilistic modeling with tensor networks, from graphical models to quantum circuits. And depending on how it goes with time, also a little bit on other recent topics on quantum assisted machine learning. So these pictures here have become rather iconographic, I suppose, on the connection between machine learning on the one hand and quantum physics on the other, where there's a huge interest in making use of machine learning ideas to learn, say, quantum to get new insights, tackling the electronic structure problem, or looking at decoding of topological quantum memories, as we've looked at recently, and we will hear a lot more about this type of very exciting endeavor. Now, there's the converse question as well of an equally big interest in identifying notions of quantum assisted machine learning in the first place, asking how we can think of notions of quantum machine learning with the hope of understanding in what way one can think of speed ups over classical algorithms, have better generalization, and so on. So this talk will be slightly at odds with this, in that we are a little bit in the middle of things, and with the exception of the outlook, are mostly concerned with what we could be called like quantum inspired ideas about classical and a bit of quantum problems. So we ask questions in two flavors: what we can learn from quantum tensor network models about probabilistic modeling, and specifically looking at expressivities, but also looking at how we can use that to learn dynamical laws from data. So in the first part of the talk, we ask, how can we think about expressivity of tensor networks, like what they represent when we think of probabilistic modeling in a kind of rather general framework. And here's the thing. Here's how the journey begins with probabilistic graphical models. So these are structures that embody probability distributions in some clever way. There's a graph that expresses conditional dependencies between random variables used in machine learning, in generative modeling, and unsupervised learning. So this is a simple example of an undirected graphical model, even though in practice they rather look like this. Oh, what's happening here? Wait. There's something funny. Oh, wait. Sorry. In practice, they rather look like this. So the point is that such an undirected graphical model finds a factorization of a joint probability distribution, and the maximum cliques in that graph correspond to one term each. It's a way of organizing probabilities with specific dependencies, and such graphical models.
So Jens, we are currently seeing just the title slide.
Really?
Yeah.
This is
strange. And now it's okay. Now it's the.
Is it better
full slide again? And now it's fine. Yeah.
Oh, okay. Sorry. Sorry. So these
check the slide. Check the slide changes.
I think it should be fine now. It should be fine. Can you see the slide changes now?
No.
We see the probabilistic graphical model.
And then can you see the tensor network?
No.
No, not yet.
How come? That's very strange. Can I say stop share and let's share again, okay?
Yep.
Share. Let's see.
Okay.
Can you see changes?
Tensor Network, I see. Maybe you can.
Oh, good. Can you see a change? Am I changing something?
No, no.
So if you don't do full screen, it works. We had the problem solved yesterday this way.
Really?
Yeah.
Oh no, how's this? But this is very strange. There's transition that's built. Or can I remove this on the right-hand side?
Well, you're sharing only a
crazy.
window, right? If you share really all of your screen, probably this works.
But now again, can you see this? Not.
Yes,
Yeah.
we can see probabilistic.
But you cannot
graphical
change
models.
the changes, right?
No.
We don't see any change. No.
This is the first time this happens.
Do you have a choice between sharing screen and sharing a
Resume
window?
share. Sharing is paused. Stop share.
So
Slideshow.
typically I share the full desktop before I go to the slideshow. I think you were sharing only a window.
Yeah, but yeah, but oh, what is this? Huh. No. Oh dear. How come? You had this problem yesterday too, or?
Yeah, so we skipped the full screen. Just show it from the whatever it is, that thing.
Okay, good. Then let's try again. But is this on your side or on my side?
It's on our side.
On your side?
I don't know where it is, but it's affecting everyone.
Okay. Okay, I'm very sorry. So okay, good. Then I hope to. Okay, sorry. This takes a bit of time. I'm sorry.
In any case, we see very well, even if you don't show the full screen. I think it's very.
No, you just okay. But how do I go back and forth then? Okay.
You click on the left.
Okay, good. And then I share my screen. Share screen, just as it is.
Yes.
Yeah.
Desktop. And then I do this. Okay.
Yes, we see
Is
the
that
full
okay?
desktop.
This
Yeah,
is
it's
fine.
perfect.
Perfect is a bit of an over-exaggeration. Anyway,
It's close
okay,
to
good.
perfect.
Close to
You
perfect.
could
Sorry, I
still try
missed.
you could still try full screen now because it might work actually.
Okay. How about this?
Can you
Can you
switch
see
the
it?
slide?
Yes.
Yes, it works. Very
Ah,
good.
wonderful.
So it's a problem of sharing the window, not the screen.
Oh, okay, good. I'm sorry. Now, good. So we are back to, okay, graphical models can be converted to factor graphs that defined on bipartite graphs of factors and variable vertices. So one factor node is created for each maximum clique, and each factor is connected to the variables of the corresponding clique. And then one can massage these factors and transforms this into what is called a tensor network shown on the right hand side. So what's this? So that's a network of tensors. So tensors are depicted as boxes sitting there, and the number of indices are depicted as legs sticking out at the right of the tensors, depending on the degree of the tensor. So this would be a tensor with two legs sticking out, like a matrix. If there's one leg sticking out, would be a vector or dual vector, and so on. So if two edges are connected, they're kind of going away, they're contracted and summed over the indices. So what's the big deal? The point is that these are structures that are enormously well understood in the quantum context, in condensed matter physics. So these one-dimensional tensor networks called matrix product states, or many paper states for good reasons, also tensor trains, they basically capture like one-dimensional, strongly correlated systems to machine precision for good reasons that I'm happy to explain, although time is a bit short for our technical lapses. So they are deep at home in understanding kind of quantum strongly correlated many-body systems, but they're increasingly understood when kind of trying to capture probabilistic modeling in way in store today when we think about this. So this is the probabilistic graphical models can be embedded, can be captured as tensor networks, giving rise to a framework to embody that type of structure. One can also think of hidden layers added to this, or think of hidden Markov models in the first place that can again be found, can be written as tensor networks. Quantum circuits, as in the title, or short quantum circuits can be written like that. One can measure upon them, and that gives rise to, again, a probabilistic modeling. That's a circuit that gives rise to probability distributions. They're called Born machines. That's, again, a way of generating probability distributions. And if one thinks about this for a minute, if one contracts these guys together, then, again, they give rise to tensor networks of this form. So tensor networks provide a kind of a general framework of capturing probability distributions in one way or the other. And there's also other examples of that type. So tensor networks can be used to represent probability distributions in one way or the other, but how precisely? So what is how can things be organized, and what is the expressive power when writing probability distribution in terms of tensor networks? So what is the expressivity of probability distributions captured in that fashion? So how can one write probability distributions as tensor networks in the first place? And there is many different ways of doing that. So one way is to think of basically a matrix product state or a tensor train, where the entries of which are non-negative real numbers. So clearly, I mean, there's the TT rank, tensor train rank, or matrix product state rank. And so clearly, if the entries of the tensors as such that are connected in this fashion, so the guys going up are the probability distributions generated, and these guys in the middle are being contracted away. So if the entries of that are non-negative real numbers in the first place, then of course one upon normalization gets a probability distribution out at the end of the day. One can also take real numbers and kind of tune them to get, with negative signs, to get a probability distribution out nevertheless. That's also an option. In principle, that could give rise to a larger class of states. And one can think of complex numbers, so fill the tensors with complex content to, again, tune them in such a fashion to get a probability distribution out. So these are already three different ways of writing probability distribution in terms of tensor trains. And again, probabilistic graphical models can be captured in this form, so that's already included in that type of picture governing probability distribution in terms of tensor network. Then there's another one that I refer to, Born machines. That's kind of the picture that relates to the short quantum circuits that I mentioned earlier, where there's a kind of a new rank, the Born rank here. Quantum physicists would know them as pure states written as density operators. So you kind of have a vector and a dual vector here that again give rise to probability distributions. Again, one can think of different fields like positive, like non-negative reals. One can fill the tensors with real numbers. One can again think of complex numbers. So these are three more different ways of representing probability distributions in terms of tensor networks. Now there's a third variant we can think of, which is locally purified states where there's a further leg in the middle, the kind of purification rank, that would be, in quantum physics, would be a locally purified state, or what is called a positive matrix product operator. So there's kind of two ranks here, a kind of TT rank and a pure rank. So that's another way of organizing probability distribution of one-dimensional tensor networks in a slightly modularized fashion, again, over different fields, namely the non-negative reals, the reals, and the complex numbers. So most of these pictures have been looked at in the past in probabilistic modeling. And the question arises, like, how are they precisely connected? What is the power of capturing things in this way in the first place? And what is the mutual expressivity of one picture versus the other? And let's not forget, I mean, each of these pictures is complete, meaning one can write an arbitrary probability distribution in either of these pictures, but some pictures may be more economical in writing the distributions than others. So what's the overhead generated from going from one picture to the other? That's kind of the question that's at stake when thinking of expressivities in this context. Now, so how are they connected? And there are surprises after all. So first of all, we look at the matrix case of how one can go in the matrix case from the various pictures, and we try to fill this table here, where on the left-hand side we see the different ranks, and on the right-hand side we ask, what is the overhead needed to go from one picture to the other? And we try to fill this picture. What this shows here, if there's a function, it says that you can embed this into the other picture at an overhead of, say, x squared or x. When there's a no, it means that there is no bound whatsoever, and there can be an unbounded overhead from going one picture to the other. And some of these entries have been known in the literature. For others, we worked very hard to prove these results. Others are rather trivial. If you go from the TT rank to the Born rank, it's just a vector and the dual vector, so you easily get a squared. Others are pretty tricky and nasty. There's even one that's open. This is the hardest matrix problem I've encountered in my entire life, I suppose. I invite you to have a look at this. It looks very innocent, but it's the question of having a matrix like in the left, where there's copy tensors here, where there's a TT rank and a Born rank, and you ask, at what overhead can you write this into the right-hand side at the expense of having a larger rank on the right-hand side? How can you embed one into the other? We've been working for weeks on that. That's one of these entries. That's still an open question, and I invite you to look at that. Anyway, so this is the picture of going from the matrix case to the expressivity setting in the matrix case. What's truly interesting is that they can be uplifted to statements for arbitrary system sizes for true expressivity questions in the many-body setting. And there's interesting surprises, of which I only take two for reasons of time, which are kind of fun. The first surprise is that going complex helps a lot, meaning using complex instead of real tensors leads to an arbitrary large and unbounded reduction in the number of parameters in the network in the system size, which is kind of surprising because you are, after all, just representing real probability distributions. Why would it help to go complex to represent real numbers? It does, and even in an unbounded fashion. So it's a clever way to think more quantum and think of complex representations, even when thinking of representing probability and distribution. That's interesting. Another surprise to us was that locally purified states, like what is coming from the quantum context for like modeling of open quantum systems or thermal quantum states, rather from that context, are better than any of the other ways of modeling classical probability distributions. And again, there's an unbounded overhead from going from one to the other. These locally purified states are the most efficient way of capturing probability distributions than any of those settings, which is again a surprise. Why would this bone rank help in representing probability distributions, but it does, and in an unbounded fashion. And there are also a couple of others. We have a kind of full diagram of the mutual expressivities of going from one picture to the other. And this expressivity is also matched by the ability to learn realistic data sets that we put together. So there on this picture here shows realistic taken data sets that are being learned in the log likelihood. So there's the above picture is the hidden Markov setting, and the others are the other ways of representing probability distributions in terms of the network. The lowest one is indeed this locally purified state that have a provably better explicit power than all of the other representations considered. So that's also matched by machine learning techniques that make use of these guys as representations. So lesson: a rigorous assessment of the expressivity can lead to surprises when looking at probabilistic modeling in terms of tensor networks. That's great. That's one of the few rigorous results known in this field, but we need much more than of that type. We need to know how can we represent things in terms of small parameters. That also applies to the quantum setting, where we would like to know what we can do with finite round quantum approximate optimization, variational quantum eigensolvers, short quantum circuits. We would want to know more, better, what things can express to see how powerful are they in modeling, in learning, in representing things. We need more of that time. There's also surprise that errors can make a difference. There was a recent paper by Gamma that showed that if you allow for small errors in approximations, things can change also somewhat and make the setting more interesting. So we need more of that type when thinking of expressive power of capturing complex structures with tensor network structures parameterized by a small number of parameters. Which brings me to the second part of the talk, of kind of developing that mindset of thinking of how we can learn dynamical laws using such structures, such kind of probabilistic modeling in terms of real tensor networks. And it's slightly different in spirit. I'm teaching classical mechanics these days, and I was talking about Kepler's laws when this guy stared into the sky and saw these funny points moving around and came up with these remarkable laws based on data. And it was a historical step, needless to say, but of course that only works if the respective laws, I mean, that's easy to say from a modern perspective, are relatively simple by staring at the data and inferring the underlying laws. This is much less obvious in systems that have a large number of degrees of freedom, where the cursive dimensionality come into play. So what is the Hamiltonian? What are the dynamical laws of these systems in the first place? And that's far from being obvious. Now, even in my courses, speaking of which, when I give my course on classical mechanics, people ask, right, the Hamiltonian function governs the system, but where do I know the Hamiltonian function from in the first place? And then I say, well, it's given by the system. And then they say, yeah, but I mean, where does it come from? There's no voice speaking to me giving this Hamiltonian. And there's a point to this. So there's an increasing effort of trying to understand how one could kind of not make modeling in the first place that can be unrealistic and complicated for complex systems, but really learning about dynamical laws from data alone. And also in the quantum context, that makes a lot of sense. We are working with Google on this. That's for another day. But to learn dynamical laws from data is clearly an important and increasingly important problem if many degrees of freedom come into play. So how can one think of doing that? Well, we can take snapshots in time and stare at the system and look at vectors of data, observing the system at different snapshots in time, and then looking at the derivatives on the right-hand side and seeing what dynamical laws match the observed data, what possibly nonlinear laws match the data that you have at the end of the day. How can one come about? Well, we can think of functions, basis functions. So think of a dictionary of basis functions and evaluate these basis functions at different snapshots in time, and think of a data matrix that capture all we have observed and then think of a coefficient matrix in terms of the same basis functions, and think how one can best match the coefficients to the data that we have observed. According to a cost function, for example, we could minimize the Frobenius norm, the Hilbert-Schmidt norm, that in this cost function sense best match what we've seen in the lab in nature as the best match for this. If we want, we can also regularize that with the one norm. That's the kind of compressed sensing mindset, to have the best, the sparse representation of the data. We can also think of threshold. Never mind, it's a way of capturing the best dynamical laws given observed data in one way or the other. Now this works very well for small system size. It's called SINDI. That finds a sparse coefficient matrix because it's regularized with this one norm that I've just mentioned, that would recover, say, the Schur circuit very well by looking at data, not making a model, but then inferring the model from the data that are being observed. Good. But, well, how about large system sizes? Then again, the curse of dimensionality comes into play. So how we can, this makes no sense for large systems. This will have an exponential effort in recovery. There's no learning of dynamical data in this sense. So how can we discover physical laws in complex systems? And again, connecting to the first part of the talk, we can think of tensorial structures. We can represent the data tensor and the coefficient matrix as structured tensors with all the legs sticking out, but this is a false friend. Don't be too safe about this. So the legs sticking out, that would be physical legs that relate to local function dictionaries now, not probability distribution. So the overall thing is a way of capturing functions, classes of functions that give rise to these possible approximations of right-hand sides of differential equations. And then one takes this tensor and chops this into pieces and makes a kind of economical, efficient way of writing these function dictionaries in the tensorial format. Now, the storage effort is very small. It's a polynomial effort. It's linear in the system size for tensor trains and matrix product states. There's a lot of fine print coming into play in that one can use of the gauge freedom to massage things into the right form. Because I promised to stay in time, I will not say so much about this, but the fine print matters to kind of keep these things at bay. But it's a way of not formulating probability distributions, but now classical functions in an organized fashion. And interestingly, this Hilbert-Schmidt norm minimization, so the best match of the data given, of the functions given the data, can be explicitly written as a pseudo-inverse that can be explicitly computed at an effort that scales linear in the system size. So using iterative singular value decompositions and exploiting the normal forms that I've not really said much about, one can in linear time find the best tensorial structure given the data instead of a p to the power of d, so an exponential effort in the system size, form and recover the dynamical laws from data. And this gives rise to an efficient recovery that works in many ways. And it's a way of representing function dictionaries, like tensorial function dictionaries in a way, and one can learn unknown data, unknown nonlinear laws from data in this fashion. This works very well in practice. Here's a kind of picture for the Fermi-Pastor-Olam model for a relatively large number of degrees of freedom, or 10 degrees of freedom, not super large, but well, I mean, it's already quite a decent system size, and it works very well in practice. So in the meantime, we've become more serious about this. We've looked at Salsa method, at rank adaptive methods of doing that. That in fact, in practice, makes a big difference of tuning the ranks appropriately. We've more deeply thought about this as a recovery problem in a compressed sensing mindset, and we've understood this quite well. In the meantime, what we have not so much understood is the expressivity question. It works extremely well, but why does it work so well? And what's the expressive power now over function dictionaries that is not so well understood? And in quantum physics, we know a lot about correlation measures and what they mean for tensor network approximations. Here, it's much less clear what correlation functions to look at to be sure that you can map out the problem in a right way. Either way, the lesson is structured tensors give rise to good results when discovering dynamical laws from data. It's kind of a fresh mindset. You learn dynamical laws. You're not trying to model, which is kind of not within reach in many settings anyway. When many degrees of freedom come into play, you stare at the data and you kind of take a learning mindset of learning the dynamical laws. And here again, in the spirit of this talk, you make use of tensorial structures here, tensorial structures over function dictionaries. Which brings me to the end of the talk, because I promised to be in time, even though my technical lapses, I again apologize. This I hate when this happens. So let's summarize and out a little bit. So this talk was according to the homework that Bart gave me on tensor networks. We've seen that this type of tensorial structure is very much appropriate when organizing function dictionaries, and we can learn dynamical laws from data. These are classical laws, but they're very much quantum inspired. The machinery used is all quantum condensed matter machinery, but used in the classical context to learn nonlinear classical laws from data. We've also looked at graphical probabilistic models, at kind of ways of structuring probability distribution that again can be written as tensor networks. So tensor networks are an embodying framework for that, also for hidden Markov models. Short quantum circuits can again be written as tensor networks, and we've seen that we can come up with first rigorous results on expressivities of tensor networks to write out probability distributions, and found surprises in that innocent-looking decompositions of tensor networks turn out to be either extremely powerful or very much expensive when writing out probability distributions. That's a nice baby step forward. We need more of that. Also in the quantum context, when we think of quantum machine learning, what can we do with short circuits? How powerful are they to do stuff, to do quantum approximate optimization, variational quantum eigensolvers? We want to know more than that. We have parameters. How powerful are the circuits when we change the parameters after? So this was the topic of this talk. So we were concerned with expressivities and what circuits, what things represent. I should also say, and that's my last word, so to say, that over the last months and weeks, we were also much concerned with the other question in that context, not so much with asking how expressive things are, what things can do, how powerful circuits are, but how we can tune the parameters in the first place. I mean, we have knobs, and what is the good rationale of turning the knobs and how to pick variation parameters in quantum circuits after all? And that's kind of the second question. There's the expressivity question, what can they do? And the second question is, how do we pick parameters in quantum machine learning approaches, in variation approaches after all? And there's two surprises I would want to mention here before I conclude. The first one is that one of the, regardless of parameter shift rules and so on, the excessively costly thing when thinking of estimating gradients from expectation values in variational circuits is to get expectation values in the first place. And what we understood is that this can be largely overcome by settings where you just shoot at the system and you take values whatever you can, you make k-shot measurements and still get unbiased estimators with proven recovery guarantees to get gradients out to make a much more efficient control over variational quantum circuits after all. So the lesson is, it's not only important to look at expressivities, but also to think of wise use of data to make updates in quantum circuits when efficiently and economically make use of data. And also recently we understood that such techniques can be used in order to learn things in a fresh fashion and kind of use variational circuit to learn other devices here, to learn probes and measurements in metrology. And this is kind of the last note that gives kind of rise to a forward-looking picture that one could use ideas of quantum machine learning to learn about other quantum systems. So think of, like, say, quantum assisted design, quantum aided quantum design, so to say, of using quantum circuits to kind of devise other quantum circuits to be used in metrology that would purely classically be highly inefficient. That's kind of as an invitation. Maybe it's a good use of using quantum machine learning ideas to learn about other quantum devices after all. And with this, I would like to very much thank you for your attention. I'm looking forward to the questions you might possibly have. And again, I apologize for this technical lapsus. I try to avoid this as much as I can. Thank you.
Thank you, Jens. Thank you very much for the great talk. We have already first questions in the chat. So Roberto, do you want to just unmute yourself and speak up?
Yes, thank you for the great talk indeed. And I was wondering if you can give an intuition behind the better expressivity of complex numbers rather than the real numbers. Is this something related to unitary evolution versus? Yeah.
I mean, the honest answer is well, yeah, well, yes and no, and more no than yes, in the sense that clearly it's a larger set. And I mean, you know, of course, it's conceivable that you kind of tune kind of complex numbers to give rise to probability distributions, and you have more knobs to turn, and that is kind of more powerful after all. But this is not so much the point. The point, exactly. This is the point. The point is that you can be more powerful in the expressive power in an exponential fashion in the system size, and that is kind of interesting. And we have quite little intuitive understanding why that happens. Also, for the other separations, say why the Born rank setting would be exponentially more powerful than other settings in the system size. So in a way, these surprises, or that things I sold as surprises, they were also generally surprising to us. And the key point is, it's not so much surprising on the matrix level, where it's kind of clear, if a couple of more knobs, you can do things a bit better. But when you uplift it to the many-body case, then it becomes truly surprising that you have exponential separations in the system size. And then, why is that? It's a proof. I mean, what can I say? Yeah, I would love to know more about this, I would say.
Sure. And actually, another small question. So I was wondering if you can give an idea of how would the tensor network approach compare with the neural network approach for the learning dynamical laws? So do you see a reason for using that instead of neural networks?
That's an interesting point. There's other works by neural networks, for example, Renato Renner's work on that and others. It's very much similar in mindset and also very different in mindset, in that what we are doing, I would say, has the kind of more say explanatory value, in the sense that it more predictive power, in that you are not learning the dynamics, but you're learning the dynamical law that gives rise to dynamics. That's kind of a subtle difference. I mean, you kind of get the right-hand side, like what Renato did. I mean, that was about like learning the behavior, and then you can make predictions what comes later. You see the planet, it's moving there, and say, oh, later the planet would be here, and you can make that prediction. What our approach is about is like you stare at the data, you get the right-hand side of differential equations, and then the product given back is the differential equation as such. So that's a bit different. So
thank you. Yeah.
Similarly aimed, but the approach is kind of different. It's more kind of a learning-inspired recovery approach than the kind of machine learning sense.
Thank you.
So Andrea would be the next. Do you want to unmute yourself?
Yes. Thank you, Jens. Very nice talk. I also had a question regarding the first part of your talk, and that's about the theorem where you mention an arbitrarily large reduction in the number of parameters. Yeah. And I was curious to know what you mean exactly by arbitrarily large. Do you mean that you can get even more than an exponential reduction?
Oh, no. This would be exponential in the system size. So it's unbounded, I would say. Sorry.
Okay.
Unbounded. But that's still surprising because, I mean, again, well, I made my point.
Thanks.
Okay, do we have more questions? Maybe I can briefly ask one. So Jens, again, for the dynamical laws, what happens if the underlying right-hand side is somehow not expressed by the basis functions you have? So you really have to start approximating.
That's a good point. Then this is the expressivity question coming into play. So of course, it kind of tries to find the best match, right? I mean, this can be good and can be a good approximation. Of course, if your function dictionary is really wildly not expressive enough, you can be really bad. That can happen too. And so we understand quite well what happens like within, like if the function dictionary is right, so how expressive things are, how things work, and what ranks to pick, and so on. This aspect of things we understand quite well. What is much less understood is like what function dictionary you would pick in the first place a priori to make a good guess of capturing the dynamical laws in the first place. So it's a very powerful approach compared to this machine learning sense mentioned earlier. Also in the sense that, I mean, one common problem in machine learning is that you learn something and you do not quite know what is learned, right? I mean, like Müller has these fun examples of learning, I don't know, properties of like classifying pictures of horses. And then you see what is being learned, and then you understand that what is being learned is the copyright symbol, because there's a kind of law that you have to equip pictures of horse with copyright symbols, and all the neural network looks at is looking at for copyright size. Or classifying Russian and American tanks, where the Russian tanks are those where the weather in the background is worse than the American weather in the background. Anyway, so there's an increasing understanding of what neural networks learn. Still, in our setting, it's very clear what is learned. So that's the big advantage. The disadvantage is what you say. It's much less obvious what good function dictionaries are in the first place. And that's something we are these days working on, like expressivities of function dictionaries that are composed of the local basis functions that give rise in the tensorial picture to the function dictionaries for the full system. So that's at stake here. It works very well, but again, this is the open homework, as I mentioned.
So do we have further questions for Jens? Yes, Bert has a question, please, Bert.
Yeah.
You have to unmute yourself.
I cannot hear you, sorry.
Yeah, so now I think, right?
Yes.
Yeah, I can hear you. Wonderful. Yeah, thank you.
Yeah, so thanks for a very nice talk.
Thank you.
I have many questions, but just one. So it comes to mind that if you have these tensor networks that can represent probability distributions,
yeah,
then in the probability distribution learning, there is also this structure learning where you if you write it as a directed graph, there is many ways to order the the variables, and you get different directed graphs, and the ordering is very important for the efficiency. And so does this, you did not mention that, but does this arise somehow also in the tensor structure? Because I guess some ordering of the variables is more efficient than others.
This is true. And yes, I only have half-baked knowledge on this, because that's something that I completely left out of this talk. You're absolutely right. But this, we basically can go over the entire talk and ask your question over all aspects of this talk. This makes a big difference, and we have some understanding, but not in full. Like, for example, for this learning dynamical laws, the same question arises. You structure them in a linear format. Why? I mean, of course, in other settings, other orderings, as you say, but that's only the tip of the iceberg. I mean, you can think of other connectivity patterns, other tensor networks, two-dimensional structures. We're just experimenting with what is called PEPs, projected entangled pair states, to recover that. There's a kind of a setting that has loops, a two-dimensional structure that works better than linear ones. But how? Half-baked knowledge.
So actually, in this,
also in the first
discovering physical laws, this ordering is very important.
Yes, but also for the first part. I mean, so what we looked at, I mean, these pictures that I showed, I mean, that work. They compare like hidden Markov models with these structures, but all of the structures mentioned are basically one-dimensional structures where there's kind of some sort of one-dimensional ordering. Again, this is the tip of the iceberg. You have to start somewhere, but of course, as you say, I mean, orderings matter, and orderings is only one way of organizing things. There's also more complex structures that one should look at. I mean, we're happy that we have rigorous results in the first place in a field that's largely driven by heuristic understanding. It is what it is.
Thank you. Thank you.
Okay, thank you.